Hey then. There we go. The thing says we're live, so you all know what that means. Hey guys, what's going on? Memes here. Yes, yes. And today, from the totally not clickbait title, meaning it's a totally clickbait title, we have the title, How Big is Universe? Yes, we are using universe in quotation marks. Why? Because we're going to use that to mean our realm of persistence, aka where we live. So what we're going to do is we're going to let some folks come on in from wherever on the internet from whence you happen to find this broadcast, or those who are joining us temporally in the future. So what we're going to do is we're going to go over, and for those that have been following the channel for a while, we've gone over some of this in different ways, different formats, bringing it up a little bit here or there, but it's like, well, if you're just putting something that may be useful or some folks may find interesting within the depths of like an hour-long lecture or something, if you don't really come out and say it, it's like, oh, people are gonna know. You might have to use advanced search things and then cruise the algorithm and not get distracted by things that make you angry, because it's not like, well, that's the current MO, because it works. But the topic for today is, again, how big is universe? When we say universe, again, we're referring to where we live, because the claim is going to be it is finite in space according to the calculations, but depending on how one views those calculations, things are actually recycling. So if you're considering the production of new space, then maybe you could view it as infinite. We are going to conjecture it is infinite in time. Okay. So we've taken pictures of this. Is what we had up here yesterday. Again, don't worry. That's not what we're talking about directly today. Although ultimately, keep note of our friend that looks like Deadpool over here. That may explain a lot. Okay. So I see some folks are joining us, and what we'll do is, okay, I've taken. Okay, I'm going to take another picture just in case if there are a few other things on here that we have added since then. Just because, hey, you want to document things as best you can. All right, let's go here. Just because we were talking about triangles a little bit earlier. Triangles, aka simplexes. What are they? They are n-dimensional triangle or a tetrahedron. Okay, we've taken a picture or updated. Now I don't feel terrible about deleting potential knowledge. Maybe again, maybe it leads nowhere, but when you start seeing a lot of things start to line up, and to the point where even some rando like me that was just paying attention to this stuff on the internet that really just grew up on the Discovery Channel, was really like science. It was my safe place. So after getting burnt out and realizing a lot of people just didn't like each other, it's like, well, I can continue screaming into the ether, which is totally not a thing. But I decided to go back to some of my roots. And since the Discovery Channel seems to be airing things about, what about dragons? Oh, this would be kind of cool and everything. It's like, now, as a longtime scaly, I can't say I'm against that, but I'm like, well, maybe let's go back into the things that I said I would never do. Because I said I should never study physics. Why? Because when I was in chemistry class, my junior year of high school, we had an uplink with a local university, my alma mater, uh, and they happened to have a reactor, cobalt 60 reactor over there. And there was a gentleman who actually ended up taking for radiation and life in college. And I asked him just a simple question. I'm like, all right, so if you can do like fission and break atoms apart and do all this stuff, what if you were to just increase the power and everything? And then I remember I just asked him a question. He took a moment. He paused. And he took a breath. He said, "Well, then theoretically, you would have created what's known as a neutron bomb, something that has a lower level explosive yield, but emits a massive amount of radiation, essentially killing all life." It was at that moment I sat there and realized I should never go into physics. It's funny how certain things seem to bring you back around. So I see some more folks are joining us. So let me finish erasing the board. and then we'll jump right into it. We'll see what's folks are commenting, see how folks' days have gone, their weeks, what different folks are up to, because that's the beauty of the internet. As much as the dumpster fire as it can be, there are some gems. Now, occasionally a good bit of mining may be required in going down potential dead ends and lost places, and perhaps those dead ends aren't actually dead ends. They're just ends where we have yet to find potential secret doors to unlock. I don't know, new cool stuff and things that humanity can do so we can get back to, I don't know, actually exploring the heavens or something useful rather than just destroying ourselves here at home. That's that's at least my goal. Just, I don't know. My slight rant as I'm finishing erasing this is simply, well, the simple solution to politics and stuff is number one, understand humans are going to human. If humans are going to human, it's very simple. If somebody truly has the courage of their convictions, then let's just legalize dueling then. Simple solution. You can either have constructive conversation or humans are going to want to fight. That's fine. I say we let them fight. Just give them the means of their own destruction. Oh, can I play a master sprinter there? Is that a funny? It's not actually really that funny. It's a terrible idea. I digress. Let me grab some caffeine. And let's see. Let's see what we got going on. All right, we have Jackson. Jackson's asking, he's the commenting, I think the max size is equal to how hard you compress the data. Well, that does sound like a good question. I don't have the initial answer. Uh, is the outside of the universe bigger than the inside? Well, that's kind of one of those. That's why I use it in quotations. I'm saying it's a universe by its definition is everything. That's why I'm like unum pluribus. For those of you that may be Americans, may recognize that as a thing that's on the quarters and stuff like that, or the inversion of that. It's like e pluribus unum, out of many, one, aka the states was supposed to form one nation under God, indivisible, all that jazz. Um, I just inverted it. Why? Out of one, many. Why? It sounds cool. Number one. Number two, if we're going to go upon even just the standard concordance model of we believe there was a very hot, dense state where the universe was much smaller and everything. And then, okay, so you've got an effective one, so to speak. Okay, out of one, and then you get the many and all of us, bada bada. It sounds right, at least there. Okay. Uh, but let's see. Oh, we got Rick. Inquiring minds want to know. Well, again, we're going to conjecture here, but I'm going to lay out a case. I think there's something to the case because we at least have evidence for perhaps some inversion there. This is more than just the I like sharing the metaphor. It's if a metaphor may actually help be an analogy to reality, and then we have to add our caveats there because we don't want to end up be like, all right, all reality is simply vibrating strings and the symphony of the cosmos. That might be true. Is that exactly what we're seeing? There's a whole bunch of okay, the strings are there, but now they're compactified because there's all these extra dimensions and stuff that we can't see and everything. But it's okay. We can test it. We just need to hit about 10 to the 30-ish Kelvin. Okay, that's, I don't know, 15, 18 magnitudes hotter. Maybe we just need to collide on the side of the solar system, the galaxy. So, maybe. Listen, hey, if somebody wants to do a string theory, that's totally fine. There's a lot of fascinating things. I'm sure it has its place. Uh, Repo Man. I've never actually watched that movie. God, I'm lacking on the pop cultural references. XYZ. The universe is at least three. Well, it's funny you mention that. Doesn't it depend on what units we're measuring by? That might make a difference. Uh, Press space still the same size. Now, I don't know, but I'm going to conjecture volume must be maintained. What does that mean? That's a good question because I'm even running through in my head now, and part of what I was gonna go over with you all guys, as far as calculations go, um, there are very, very interesting things. But Rick's commenting, indivisible is uncompressed at. Oh, I like that. I like that. That makes a lot of sense. But well, that's magnitude of scale. I think that's what we're going to have to do. Oh God, these are a lot of. That's the thing. What is the definition of is? So let's get into a little bit of what we might be talking about. All right. So before, as we've gone across, I'm going to do. I know. I'm beating the old whiteboard. Let's go with blue. All right. We got our blue marker here. All right. So we need some stuff. All right. So we got some stuff over here. These are our ingredients. Ingredients. Really can't spell. All right. And then we got all right. So our ingredients are time, space, charge, mass, and temperature. Okay. So, oh God, temperature. Gotcha. There we go. Wow. You can tell. Totally got a C in spelling in like the third grade. All right. So basically, these are the dimensional ingredients of reality. So if one was to attempt to build a universe, we're going to need to account for these five things, not an infinite number of things, at least these five things. Now, okay, I'm going to caveat that infinite. Time might be just be going around and around, my friend. But for this, these are our building blocks. Why? Because if you go into code data, you go through all the different constants of nature, you're going to find those of them that have dimensionful quantities, because there's some dimensionless things like the fine structure constant, etc. Um, but for those with dimensionful magnitudes, they are constructed out of these five ingredients. And even the dimensionless ones, even the fine structure constant. It's if you're going to do that, what do you have? It's a dimensionless thing, but it's elementary charge squared over 4 pi h bar c and then e naught. Okay, that equals alpha, and that's dimensionless. But you get a unit of charge squared. Long story short, since it's dimensionless, this ends up being charge squared down here. But beforehand, it's 4 pi, so you get a spherical thing. You get h bar, that's mass area rate. So that's mass times length squared all over time. And then you get c, well, that's a speed, the speed of light in a vacuum. So that's length divided by time. And you got e naught, which, oh God, this is the one that gets me. Okay, so it's going to have mass in the denominator because it cancels out with h bar. Then you get the what is it, time. So it's got to have time in the numerator, and then it's got the oh yeah, time twice and then two charge. Okay, so that will make it charge squared. Okay, and the Planck charge is what is it? Square root of 2 pi and then times 2, yada yada. So that's where we get the 4 pi from. Okay. See, even a noob like me can start to learn some dimensional analysis. It's just you just follow the logic. Okay, so why am I saying this? I'm supposed to be talking about size. Okay, well, interestingly enough, that represents a dimensionless thing. If the other things there are going to be dimensionful things, well, what if we did some calculations? What if, okay, the universe in which we live, the best way to do this. All right. Go with the standard concordance model. I'm not saying this is exactly what happened, but we believe there's a hot, dense state. All right, let's go redonkulously small. So we're gonna put a point here in the center. Again, this does have magnitude, but that's a really small point. And if we believe we're gonna end up with ginormous universe, Come on, marker. Come on, marker. If I press down harder, it leaves better marks. There we go. All right. All right. Big, ginormous. Oh my God, it kind of looks like a minion or a potato. So, all right, well, we'll take our potato universe here. Okay. More of an egg, really. But, okay. Oh, and we got Laszlo. Laszlo, I haven't seen you for ages. How you doing, my friend? Yes, yes, I'm continuing blasphemy like normal. I should probably sit on this. There we go. Let me see our delicious egg-shaped universe. Yeah, yeah, yes, yes, Rick. Nanu, nanu. I forget if that was God. People from that like Star Trek are they're gonna run me through the grater all. Good to hear. All right, all right. So where will we go? Okay. So probably all right. I have a ridiculously small point. Okay. Okay. Ridiculously small, ridiculously big. All right. Now, the interesting thing is if you look at some of these things, it's like, all right, well, we've got these units here. I should probably actually finish that. Now, our elementary units, and these are things that we get from calculation when we compare the different constants in nature. Typically, it's a square root form of some combination of big G, the Newtonian gravitational constant, h bar related to a particular power of the speed of light. Okay. But we end up getting out units. And for the time, we get the Planck time, small t sub p. For space, we get a unit of length, small l sub p, the Planck length. Charge, we get a unit of charge, q sub p, the Planck charge. Unit of mass with the Planck mass, small m sub p. And then we get the Planck temperature, which is very hot, so it's big T sub p for Planck temperature. Okay, so we have these units. And I know Rick is in the chat. Rick is one of the people that has highlighted the importance of looking at things from a different perspective, perhaps inverting them, because it may yield additional information or help brains like ours, our human brains, better comprehend what might be going on. Okay, so you can do something kind of like this. You can do, all right, let's expand this. All right, let's do 1 over LP. But more than that, that's going to give us an inverse dimension of length. What if we were going to claim, let's say, hypothetically, let's say there was really small, dense, pointish type area. Maybe it's, I don't know, the toroidal projection of the hyperbolic figure eight knot, or pick your torus there, and we're going to invert it. It's going to invert into a hypersphere. However that might happen. Okay. Again, conjecture, but we want some dimensions here. So let's go from 1 to, how about this? Meters squared. Why do I do this? Because that gives us a very useful number. Don't worry, I'm not holding out on you. Not too much. All right. We'll get there in just a moment. So we'll go to friend Wolfram. All right. Let's share our screen with the class. All right. You can go over here. All right. So we'll simply clear that out, and we'll just put in right what we had there. Meters squared divided by Planck length. Boom. Okay. And it gives us a number. Oh, look. And we're looking for meters. Wow, that's a very big number. Because the Planck length is about 10 to the minus 35 meters. So if you do the inverse of the Planck length with that meter square dimensions, you're going to get out the dimensions of meters. And it's the inverse of its magnitude, which is 6.187. 6.187 times 10 to the 34 meters. Okay. So we're basically saying that is our radius. Why? Because we work with radii. So now, and again, what is this? Oh, you get this number. Does this number do anything for us? Oh, my friends, it does. So we'll go over here, and then let's see. I get the. Okay, I already got. Here we go. I've already got written now. All right. So this is. Need to add. There we go. All right. So since we live in what appears to be a four-dimensional space-time, three dimensions of space, one dimension at a time, sine convection, people argue over and everything. Yes, it seems to work. Could be totally wrong. All right, so what we're doing here is we're looking for a dimension four hypersphere. So a four-dimensional hypersphere of a radius, the inverse magnitude of the Planck length in meters. Why? Because if the Planck length is a minimum unit of length, if we invert it, is it really that far a stretch, so to speak, for it to be the maximum unit of length, or at least in regards to our spherical cow-like design? Because as we went over yesterday, listen, there ain't no such thing as an actual spherical cow. Maybe there exists in some thought realm a precise spherical cow. That's the physicist's way of saying, all right, we will grant you a circle. You can assume it's a true circle, even if there is no true circle or perhaps a maximum magnitude for circularness. It was a very weird thing to say. Can't confirm if it's true, but it might be true. Who knows? All right. So we've set a magnitude over there. Okay, so I input the calculations. But let's get to it. All right. So we're assuming a radii of 1 over the Planck length, aka meter squared over the Planck length. Okay, to get it in the correct dimensions. All right, so I get this equation here and all that jazz there. And then keep note of this number. Keep note of this number. This is one of the most useful numbers in our realm of persistence, I would claim. Okay. So we'll get out of that. We get the diameter. So basically just 2 of the number that we put in. Okay. 1.23 times 10 to the 35 meters. And then if you notice, the content in 4 dimensions is this ginormous number here, 7 times 10 to the 139 meters to the fourth. And we got 4.6 times 10 to the 105 cubic meters and stuff for the hypersurface area. Again, one might ask, where do we live? Do we live in the delicious 4-dimensional center? Or are we in the crispy candy 3-dimensional shell and just the continuation, iteration of each tick tock of universe's clock is the inexorable computation of reality? Just spitballing. You're all a homotopy. Okay. Why is this interesting? Okay. So let's go back. So we got a ginormous number. Okay. So we've got this over here. We're going to claim this is the radii. And then where do we go from here? We have this little point. What is this point? Now, our current estimates is right now, if we were in universe as we currently have it, it's about 10 to the minus 8 meters. But was it always something like that? Now, a very interesting calculation you can do, which if you, such good comments. Okay. So if you do a very interesting thing, so let's go back over here. And, all right. So we're going to go to that. I like calling this the hypersphere operator. This 3.8, 279 times 10 to the 69. We go over here. It's a very interesting thing. We take a look at that number. Okay. We open another tab. We do basically the exact same thing we did before, except we're going to use some brackets. Meters over Planck length. Okay, I think I need to do it this way. Yeah. No, I think. Well, let's see what happens. Forget this guy. Ah, here we go. Does this number look familiar? 3.828 times 10 to the 69. Oh, 3.8279 times 10 to the 69. That looks like pretty effectively an 8 there. It's basically the inverse of the Planck length squared. Yes, that is our hypersphere operator, which the interesting thing is we just take this base number here and we were to say, let's just do some wizardry. We just multiply it by the Planck length. Oh, excuse me, Planck mass. All right. Oh, well, that's effectively the number you get if you do that whole Planck force that Dr. Pius and Rick have both spoken about. That if you assume the Planck force is going to be consistent for generating mass and everything, if you had a radius, you could plug it into this formula, and coincidentally, you get the same number. The the same number for the estimated mass of the universe from effectively over this. WTF, mate? That's a very interesting thing. Okay. He's speculating here. What is actually here? Okay. So whilst going down many a Wolfram hole, you start to notice there are these other Planck things, not just our five-dimensional ingredients there. There are other combinations of things, which always leads to a question. Why are those things the way they're at? Let's take a look at another friend here. There's one that we call the Planck density. Planck density. Okay. So okay, you got your standard for C5 over big G squared times H bar. Okay, gives you this crazy 5 times 10 to the 96 kilograms per cubic meter. That is crazy. What is it? It's literally just the Planck length divided by, excuse me, Planck mass divided by the Planck length cubed. Your cube is in that, but that's got a ginormous number. Now, why am I just showing you this random ginormous number? Means you have to have a point. I can't necessarily say it's a point, but it appears to be a volumetric area because if you take this whole thing, this 8.33 times 10 to the 61 kilograms, and then we divide it by the Planck density, we get a very familiar friend here in a slightly different form. 1.616 times 10 to the minus 35 meters cubed. Now, for those that haven't spent all the time that I have, the Planck length is 1.616 times 10 to the minus 35 meters. Wait a second. Hold on. These numbers look suspiciously the same. They have like the first digits, they have the same negative magnitude. This one just happens to be a unit of length, so it's just in meters. This is a cubic thing right here. This is in meters cubed. It's the Planck length in cubic meters when you take the estimated mass of the universe and you divide it by the Planck density. We appear to have found a thing of one. But that's not good enough. We must continue, my friends. This is a volumetric term. We over here we're talking about lengths. So what is this length? So how would you go about figuring out this whole jazz? Well, since it's in meters cubed, we simply just raise it to 1/3. We're taking the third root because we want to get that volumetric term out. We want to figure out what your elementary unit of universal length at that time would be. All right, so about 2.5 times 10 to the minus 12 meters, and it's approximately, it looks like it's just a hair above the electron Compton wavelength with just mass. So apparently, if we were to take the estimated mass of the entire universe, so to speak, the estimated mass unit, and again, there's going to be some more energy in there because there's some more stuff going on, and you crunch it all the way down, you divide it by the Planck density, you end up with about a Compton wavelength of all the mass in the universe. I mean, that sounds pretty small. I was not expecting that one to pop in there. It's, but it's a very interesting thing. But let's see. Oh my God, this Rick, I totally used that. I totally said that on like I think Hank Green or something on Blue Sky. I'm just like, Mother Earth is a silica-based life form. I like that. But let's see, what do we got? Oh, yeah, yep. No, Jack's pointing out we appear to be finding life all over in places like digging down in the earth. We're not able to get any further. It's like we're drilling into a hot, gooey, almost seems kind of like skin in a way, and we're finding life in places that we couldn't survive. Um, it's a very fascinating thing. Uh, da- 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 oh, hey Dan. Yes, three dimensions of space or length. Basically, we appear volumetrically. I understand I'm on a two-dimensional screen here, and there are individual pixels here, and eyes are picking up photons, and ears are picking up whatever vibrational frequencies that I might be putting out that may be slightly coherent. Okay, but all right. So let's get back to. So coincidentally, if we were to have some initial conditions, so to speak, and again, highly speculative, I wasn't there then, but if we were to take total mass, so let's just do this. So uh, sum of uh, mass, and then we come out to be about uh, 10 to the 61 kg. We divide that by Planck density, so that's let's do big D. So P density Planck that equals uh, L magnitude of LP meters cubed. Okay, magnitude. There we go. Okay, meters cubed. Okay. I mean, I thought that was an interesting coincidence. It seems to happen to because I had no idea where the Planck density comes from. Because that's also they I think that's where what is it? Crisis in cosmology or no, the vacuum catastrophe. Because what is it? If we do the vacuum catastrophe, it's hold on, let's go back to the Planck density because the Planck density that's mass divided by 3 units of length. So if we just multiply it by c squared, we're getting the energy equivalent. Okay. So then we get, oh, look, the Planck pressure. That's at 4.6 times 10 to the 113 pascals, which apparently the energy in the vacuum is a little bit less than that. It's about like five-ish protons or so per cubic meter. It's not that high. However, if we were to rewind back to a very hot dense state, let's just say if the universe as we know it was at about the magnitude of a Planck length in meters cubed, the pressure would be like that. Just according to the calculations there. So what are we getting that? All right. I'm gonna get at that. This universe, small u, because I don't know here. Uh, uh, dragons? I don't know. Maybe there's dragons. All right. So universe, small u. Universe rotations equals big. There we go. BIG, all capitals. Why? Because it's big. I mean, you can listen. I can speak all this day. I can give you the full thing with like I don't know, this whole 60 digits of that's closed form for the Planck mass and go over all these digits. Is it really going to make a difference? But the standard person, it's like, oh, I memorized all the derivatives. Actually, maybe that's a pretty cool thing. But ginormous. It's big, big, because the current estimates from the concordance model. So concordance model is about 10 to the 26 meters. All right. So 10 to the 26, that's freaking ginormous. 10 to the 34 meters, big, big, very, very big. So versus, so basically it's about 10 to the 8. So about 8 orders of magnitude difference. And the interesting thing is, when you go through all these, and perhaps it shouldn't be a surprise, but when you start going through, like, all right, if you do like 10 to the 61 kilograms, you're going to find, that's about 8 orders of magnitude, the mass of our observable universe. And most of these are right about at 8 orders of magnitude difference. So there does seem to be some mirroring going on. Should that be really surprising? Probably not. But let's see. All right, so we got a radius here. We've already answered the question about how big is you. Oh, and to be fair, if what some of what's conjectured in eternal cyclic cosmology or any of those cyclic models is true, it means that most likely things are going to go out like this. And eventually, as we form larger and larger structures and everything over here, things are basically just going to kind of recycle themselves. And then we're just going to loop around. So if you want to say, if we're going to consider space in that fact as being regenerated, is created, or some configuration of matter is becoming space-time, photons are becoming space-time, whatever's going on, we believe, or at least right now, according to the model, we've got some sort of figure-8 type action going on in there. Because if we do have some form of a figure-8 knot style action there, giving rise to an external toroidal surface there, and that's going around and it's doing its little thing and gets sucked up that vortex, all right? Stuff comes in, stuff goes out. Never a miscommunication. Now, what would that mean? It looks like, number one, we're adding some heat because whatever's being compressed down to about 10 to the minus 18 meters, roughly about the charge radius of a neutron, going to be compressed down really, really tight. And let's just say you've got like a supermassive, hypermassive black hole. It's being slurped out in there. It's being spit out as, I don't know, stream of neutrons. If you happen to have neutrons coming out, well, guess what? After about 14 and a half minutes, those dudes are going to decay into protons, electrons, antineutrinos. You're getting a lot of your constituent parts. Again, that's rampant conjecture on my part. But if you just want to believe that, all right, once you get to a certain temperature and stuff, all the matter and antimatter should kind of poof into reality, we can do that too. But essentially, irregardless of that, I'm a Bostonian, and we're allowed to say irregardless. Regardless of that, basically, if you got things circling around, all right, you're adding temperature, so you're adding some form of convection. If this son of a gun is spinning at all, you might start to be adding some angular momentum to the thing. So this dude is kind of going around and going around. You might add a gradient here, which would be quite high in the center if we're going to assume some form of superfluidity or even just the standard curvature of space-time. You got something going really fast and stuff's going to add curvature, but then that gradient's going to extend. And hypothetically, if you were starting from an extremely small, dense, hot state and you had to be expanding out, whether or not there was inflation, if you just have some form of expansion to take this actual form and magnitude, you got this little thing sucking things in, putting them out. Guess what? That gradient is probably going to add some ripples. You're probably going to see some distortions. And if you've ever seen them do the Newton's bucket experiment, so the whole Newton's bucket is you take a bucket, you fill it with water, you put it on a rope, and you just start spinning it. start spinning, and the water will stay still for a little while, and after a while, it's going to have the centrifugal force or whatever the actual centrifugal force is, because people argue about that. You're going to have the water start to crawl up the sides. Well, you got gravity and stuff. Well, that's just normally what happens. You got kind of like that inertia thingy happening. Okay. But if you do that with superfluid helium, if you were to have it under idealized lab conditions and everything, and you start spinning a bucket full of superfluid helium, it doesn't normally just crawl up the sides. Well, I mean, if you just leave it there, it occasionally will crawl up the sides, but that's another issue. But if you start spinning it, what you'll find happening is rather than having it just one vortex, you're going to see different vortices just taking away that angular momentum, and they'll like start to appear throughout the whole dang thing. It's such a crazy thing that I think even Professor Feynman at one point, when they actually did the experiment, they showed that he just kind of it was just kind of there, and he's like, I dreamt of that 20 years ago, but I was too afraid to speak it because I thought people would think I was crazy. Something along those lines. He's like, he literally dreamt of the exact phenomena, but he's like, I thought people would make fun of him. This is Dick Feynman, and Dick Feynman's like one of the top level trolls in all of physics history, and even he was too afraid to say it. So I'm sure I'm butchering that story, but I did hear that story, and I'm like, that doesn't surprise me because it's also not the first time I've heard people tell me that things have come to them in dreams and stuff. It's like, well, why did I discount that? Maybe it came to you in a dream. Maybe it came down from up above, the almighty, the all-encompassing universe itself. Some dragon outside our realm? I don't know. But just because it comes to you in a dream doesn't mean there might not be something there. Maybe there's something worth exploring. All right, where was I at in my ramble? Ah, yes, size. All right. The recap for all of those, we're just joining. How big is universe? Big, big. According to the generalized calculations here, our observable universe is about 10 to the 26 meters. That's probably somewhere right on the border of the point there. All right. If we were to assume this is the whole dang thing, about 10 to the 34. We get about 8 orders of magnitude, or take the universe, multiply by 10 raised to the power. Basically, add about 8 zeros on to the current calculations. That's freaking crazy. Like 10, what is it? Million is 6 digits. All right, so it's like 100 million times larger than our current estimates. Oh, that sounds good because people 100 million. I can figure that. Now you're just going to multiply it by the actual size of the universe, which is already ridiculous. Okay, but when we do the calculations too, especially when we plug this in, we'll go back there. When we plug it into our hypersphere operator, which is essentially just meters squared over, or meters cubed over Planck length squared. I believe that's how we did it there, or we just did. I think we just did that. Oh yeah, meters squared over Planck length, and that was all squared. Okay, that's what it was. See, I can go through that. So, well, if the universe is expand now, here's the interesting thing. According to this, do we really need expansion right now? If we just apply fluid dynamics, you got a hot thing, and you got some spin going on. Isn't most of the stuff just going to go into like the generalized outside, flow through, and flow back around? Only we had a picture of that. Coincidentally, I have a picture of that. There we go, ECC. I'm glad I took a picture of this one. Okay, so here we go. Let's go back to so right over here. Okay, we got our thing. Remember, this is not to scale. I think that's important here. What do we got here? All right. So we got our standard things. We got our conjectured, a little space in the center. And then this is essentially what we're claiming was if there was an extremely hot, dense press start ignition state in which All of a sudden, we went from this to we needed to go out to our current size. All right, this would have been about the Planck length in cubic meters, aka about the Compton wavelength of the electron, about 10 to the negative 12. Okay. We believe currently we're at about 6 times 10 to the 34, aka meters squared over the Planck length for our radius. Okay. So what happens if you press start? Because we always see these drawings of like universe. It's like all of a sudden we're getting maybe there's an inflationary period around here and it's expanding and it seems pretty flat and it just keeps expanding. So maybe it's simply just me being probably on the spectrum a decent bit, but something about that didn't seem enough symmetrical. So I just simply am like, all right. So what happens if you just start here and we just complete the circle, so to speak, or in this case, hypersphere? So whatever's getting out this way, if it's hot, and especially if we do have some rotation, that's why we got this little arrow over here. So we got some rotation going on, and we've got hot stuff, and it's being rotated. Doesn't that sound similar to some other things we know? I don't know. I just know that in middle school, the 2 liter bottle trick. You take a 2 liter bottle, you fill it with some fluid, you screw two of them together, you give it a little bit of spin, and it starts making a vortex. Like, I think that's pretty cool. So what if we had something like this and it was basically doing the same thing, especially if you had an input and things are getting very hot and dense and they're going out, and as they cool, they're going to go around, especially if you have a point as a sink. Because in electromagnetism, you have sources and sinks. That's how we conceptualize electromagnetism, in that, all right, we consider some form of a point particle or something. It's got these field lines coming out and then they're looping back around. It's basically just the same thing. You're just applying thermodynamics to it. Because if you did have a maximum thing, eventually, well, you're just going to have effects of gravity. And if you did have everything in balance, you're going to have stuff coming out. It's going to be under the rotation. It's going to just kind of loop back around and then go back into another vortex at the end of the cycle. Okay. So that is very rampant conjecture there. Now, that just happens to come out from the calculations. And again, it's maybe this is a misinterpretation, but it's an alternative interpretation, which at this point, number one, if universe is much more ginormous than we previously thought, then might it be possible that our realm of persistence where we live might also be a little bit older? Yes. I'm going to make the bold claim that I think universe is older than 14 billion years. Now, locally, we may rewind back about 14 billion, and that's fine. How can we justify this? We have 10 to the 26 meters. I don't know. Maybe if you have a hyperblasted black hole or a galaxy much more ginormous than where we live right now, if that were sucked in and sped out, we're just going to be kind of floating along. Some may refer to those as bubble universes within a much vaster cosmos. I just prefer general universe to mean everything, and that's why I prefer a realm of persistence, because in theory, you might be able to get to most of these places here. Now, you might not be alive unless you have some form of high-level cryogenic or stasis control, or you achieve immortality or something, some like the first ones in Babylon 5, or at least the first one. Oh, hey, Mark. It's, XYZ. That's very interesting, because I was bordering on the topic for today. We'll probably do that tomorrow, because the CMB, the cosmic microwave background, interestingly enough, is apparently an axis of evil. Apparently, the spot that we're heading towards in general for the movement is a little bit colder. From whence we came is a little bit warmer. Now, I'm just saying, if I'm going to believe the BS coming out of my own mouth, isn't that what we would expect? If we were to be generated at some point, going out into perhaps a cooler, denser, letting things kind of just expand out, kind of like I think we did in this video before, a couple of food coloring drops, and then you get the little vortex and stuff coming around. Might that explain the phenomenon? Because now if we just need to apply the Navier-Stokes, which apparently I don't think anybody solved except for maybe that gentleman over in Israel that I found the copy of, and oh God, he's very old. I hope he's still alive. I meant to reach out to him for a couple of years. But essentially, if we can just apply fluid dynamics and just the standard thing you learn in a kitchen in middle school, does because if you've got stuff getting compressed, it's going out. Isn't that going to almost apply a boost? It's going to be some form of mysterious invisible energy pushing the cosmos apart and everything. But at the same time, you're going to have something also acting as a sink, kind of bringing things together and also maybe tugging them a little bit in other directions. I mean, I'm not, I have no idea if that would maybe affect some of our observations, why we can't get them to kind of line up because we're assuming certain things. But at least according to this, and again, I just without doing any of the heavy fluid dynamic calculations or using any of the $30,000 software that's out there, um, just these basic actions could account for like about 70% of the unknown in the universe. Now, I'm not saying it could explain anything else, but if you can figure out 70% of everything that people don't know, that seems like an improvement. So, and again, we're just putting this back together. Yeah, yes, nerdy. We have pictures here. Yes. Well, Dan, that's how I look at it. Just because I'm like, all right, what are the things that we know? And then, all right, we take the things that we know, we take the measurements we have, we run the calculations, and we do make assumptions. We have axioms in what we have there. And I think it's very important that we list those axioms. And again, I'm very biased on this one. This is the poster that I had to Mystify SciCon. Didn't really talk about it much. They're mostly in the lobby of the night before with the guys like Dan. Uh, but it's interesting just because I'm like, all right, let me try to account for as many things because this poster is even called just a physical explanation for dark energy. That was all. Because what you could also go through and oh yes, we have citations. We have citations, although I don't think I actually cited. I think I cited the Stephen Wolfram video. I don't think I cited his paper. No, I've got Dennis Sharma, Jonathan Thay's paper. And then most of it's just pictures I was stealing from Wikipedia and giving credit to. Um, okay. So, but basically, we're trying to account for as much as possible. I'm looking at the model. I'm like, all right, so if we're going to assume that there is some geometric form that is a minimal thing, but an integral part of our reality, we just stick in the center there. Now, if by its nature it has rotation, according to Professor Seligman, and if it's kind of like literally, it's like you take a torus, kind of like a solid torus, and then you were to have a worm kind of eat its way through from one pole, looping around in a figure eight to another, some might say that could be considered a wormhole. Now, is that exactly what it is? I don't know. All I know is that son of a gun is sucking things up fast enough. If you have accelerating space time, you don't we technically believe that energy things it actually starts to create actual particles popping out of the vacuum and stuff. So I'm like, even if you had a very sparse space time, you might actually be getting a lot of stuff going in there. And then if you're feeding it with any type of particle, mass, this, that, the other thing, maybe photons, you're basically just bringing stuff in. It's going all the way to one side. It's going under a Mobius transformation. It's going all the way to the other side. I don't know. Is that how you square light to get mass? Is that y equals mc squared? I don't know. Uh, we've really gone off the farm with conjecture tonight. Then again, hey, maybe we haven't gone far enough. But the thing that we're just trying to detail here is, I know. Let's see. Hey, Bone. Oh, we got Bone and David. Yes. Now we're just talking about. Oh, oh, oh. Bone is back in dog form. Okay. Happy puppy, Bone. Good to see you. It's. Pardon me, but all right. All right. So the moral of the story is just according to these calculations here, basically the magnitude of the universe, it's about 8 orders of magnitude larger than according to the concordance model that a lot of folks subscribe to. You can subscribe, you can believe whatever you want. I'm just trying to provide explanations for as much as possible with as few changes as we can. What's the primary change? Basically, you got the complement of the hyperbolic figure eight knot in the center, basically acting as a form of a hyperpump. Citation Cowley Fisher, because that's the first person that I heard that term from. So acting as a hyperpump to basically just keep the whole thing going. You apply all your forces, you let gravity do its thing, bada boom, bada bing, you may have an eternal system there. Okay. The other reason why is there was a Wolfram thing, and we could probably wrap up with that just because this is not something that you normally would have heard unless you listen to the gossip of a former particle physicist, apparently. But back in the 70s and 80s, Professor Wolfram was working with physicist Jan Amjorn, and they did some calculations and stuff, and then they published it and stuff. And then a few years go by, and what ended up happening is a science fiction writer and also who happened to be a physicist, Robert Ford. He basically called up Professor Wolfman. He's like, oh, are you sure your calculations are correct? He's like, well, yeah, I think my calculations are correct. He's like, if your calculations are correct, there must exist somewhere within reality basically a perpetual motion style machine. And then Stephen Wolfman be like, oh, I looked at what he said and he's right. And I'm like, wait, you just casually just said, I looked at his claim and he's right. Not okay, maybe under some idea. He's like, he's right. And then he goes into it and he's like, well, I don't think necessarily you could do that with matter, because matter, you would need perfect opacity to block out all the different wavelengths of light and everything like that. However, he did say you suspect you could do that through a particular field configuration. And I'm just like, now, okay, I'm happy to say, like, all right, we can't construct a perpetual motion machine. However, if there was to be a system that would qualify of a Cardano machine of technically the third type, they usually say modified 2, but 3 is, I believe, more appropriate. But couldn't you just have the field configuration of where we live? Because in that case, well, if you're going to go into perpetuality, I don't know. Wouldn't it be the system itself if we were going to have something perpetual? I don't know. It's also very pretty. And again, very biased just because I'm the one talking about it. Of course, you're going to be biased for whatever you're talking about. I mean, isn't that just human nature? Perpetual motion. Let me just bring that up. Okay, so let's see. Okay, we'll do this. Oh, because I actually made. Okay, this I'm gonna show a little. Thing because I actually did some code, and by did some code I mean I had ChatGPT help me, and then I cleaned up some of it. But here's the story. Let's get into it.
Long ago with my friend Jan. Let's see. Memes asks, has anyone ever done further investigation into the paper that I wrote long ago with my friend Jan Ambjorn on the thermodynamics of the vacuum? Yeah, well, so that was in 1981, I think. It was when I was still a card-carrying particle physicist, sort of. Wrote a couple of papers called Properties of the Vacuum. And there's one called Mechanical, one called Electrodynamic. And we promised a part 3, which was which was about gravitational properties of the vacuum. We never wrote part 3. We got many, many requests over the years for part 3. And I think I finally figured out a year or two ago what part 3 should talk about. But at the time, back in the beginning of the 1980s, was a time when gravitational properties of the vacuum were definitely things that were sort of emerging through studies of Hawking radiation, black holes, other kinds of things like this. But we didn't.
Just a note, as somebody that actually read that paper, I can see why Stephen Wolfram created Mathematica. There was a lot of mathematics in that I'm like, oh my God, he did this all before like Mathematica and like Wolfram Alpha was a thing. You're looking at all the notation, the symbols, the calculations. I see why he built the tools. All right, let's continue. Continue, Professor.
Sort of know how that worked. I think we now do know how that works. And I keep on telling Jan and Bjorn that we should, I keep on saying, let's spend a weekend and try and write part 3. And I don't think he takes me seriously because, he's an academic and academics don't write papers, substantial papers in a weekend. It's only crazy people like me who've spent decades building tools and so on, that it becomes even conceivable to actually do significant scientific work in a weekend. But in any case, if you ask what became of those papers, the most interesting thing that became of them, they were studying kind of what happens to a little piece of vacuum that's put in a box. And actually, a chap called Robert Forward pointed out quite a few years after we'd written those papers, said, you know what, the way that you've set this up, there's been as you change the shape of this box, by the way, the big effect is a thing called the Casimir effect, which is that if you have two big metal plates, and they're very close together, and it's all in the vacuum, there's a small force of attraction between those metal plates. The origin of that is that in quantum field theory, there are always vacuum fluctuations. There are always 0-point fluctuations of the field for example, the electromagnetic field. There's always little electron-positron pairs that are coming up and disappearing in short amounts of time. There are always these fluctuations in the electromagnetic field. But it turns out between the plates, the presence of those plates is cutting out certain low frequency, long wavelength fluctuations of the field. So there are fewer fluctuations of the field between the plates than there are outside the plates. And that's sort of why there's a force of attraction even in the vacuum between those plates, because sort of the vacuum isn't quite the same between the plates because you've cut out these low frequency modes by the fact that the plates are there. Well, that argument about, that sort of intuitive argument doesn't quite work, because if you have a metal box, so to speak, that's a whole three-dimensional box, actually the force of the Casimir effect goes to create pressure outwards in that field, which is what Jan and I did back in 1981. And we kind of analyzed it for arbitrary shapes of boxes. And what Robert Forward then pointed out was if you take our results on these shapes of boxes, you kind of squidge them around, you will discover that there's a closed cycle, very much like Carnot's cycle, a closed cycle of.
So to be fair, I got the dimensions in this box. The general concept of just you're able to squidge and everything, and then basically within those fluctuations, you're doing things theoretically that you're basically just kind of mining energy from vacuum fluctuations. But I got two of the dimensions wrong. The concept is generally the same.
Of action to this machine in the vacuum, so to speak. If you change the shape of this box in the vacuum, you can go through a closed cycle and extract energy from the vacuum. And so he wrote some papers. He was also a science fiction writer, and I think he put this in his science fiction books as well. But he wrote papers about kind of extracting energy from 0-point energy of the vacuum. And it even there were some studies of kind of spacecraft propulsion based on 0-point energy. I think the main place where that's landed is in dialogue in various science fiction movies about sort of 0-point energy as a source of
Okay. The long story is it gets to the point where it's like, all right, it never really made it into science fact, but it totally made it into science fiction. And it's like, are you serious? This is an actual thing. Like, we've been doing this in sci-fi. Like, have many people been doing much more research into this? You don't hear about it a lot, so that's just a very fascinating thing. So let me just see.
Imagine kind of a field that is constructed to make sort of this box that will constrain the vacuum. It's worth looking at, actually. It's kind of that would be the ultimate irony if on the 200th anniversary of Carnot's argument that where he used the argument that there can be no perpetual motion machine, if in fact one figures out how to construct a perpetual motion machine that it continually extracts energy from the vacuum.
Now again, I'm not saying that we could create something like that, but maybe we live in something like that. But we've been going for more than an hour, so that's about all we got right now. So hey, take care of yourselves, everyone, and stay safe out there. It's a crazy world, but here's hoping 2025 will help us survive. Oh, hey, purple. It's you know what? I think maybe that's one of the reasons why meditation is useful. Then again, whatever you happen to do, just do it awesomely. Peace out, everybody.